Okay, so here's where we were last time. We were talking about parametric curves. Remember, the big idea of parametric curves is that it just gives position as a function of time. So position, could represent by a position vector. You can think of that as just, well, it's the x and y coordinates. It tells you, where you are in terms of its coordinates, right? As a function of time, right? Which is the variable that goes in to the function to give you position. Now, I want to call your attention to one thing. These pictures that we draw here, these curves, these are not graphs. We're going to spend some time a little bit later on, very soon actually, talking about specifically what is a graph and what's not a graph. But let me just remind you from way back when, the idea when, if you graph a function, well, the way it's done in the Calc 1 class, for example, is, well, you put the input variable on the horizontal axis and the output variable on the vertical axis. So the pictures that you draw are in a world where the coordinates are the input and output variables. That's not what's happening here, right? Both of these axes are output variables. There is no t-axis on this picture. T is the input variable, right? So this picture is fundamentally different than graphs, and as a result, we shouldn't sort of expect to be able to use intuition that we have about how graphs. What does that mean about the function? Algebraically, what's the connection between the algebra and the geometry of the picture? That kind of intuition that we had for graphs, out the window for parametric curves. Totally different. Okay, so just keep that in mind. We're going to see some examples of that pretty soon. So we talked about, one example, kind of two examples of parametric curves and what they look like. In both cases, an easy way to do it is to take the parametric curve and try to figure out what algebra do all of the points on the parametric curve satisfy. Now, it's not because somehow this is better algebra and this is, kind of worse algebra. That's not the case. It's just that they're different, and this one happens to be more familiar, right? So this is a familiar bit of algebra that in its way describes a circle. But this also describes the circle, just in a different and less familiar sort of a way. Okay. In this next case, again, that we saw last time, here's a parameterization. Here's some corresponding algebra. This is the equation of the curve. This is a parameterization of the curve. They're different. They describe the curve in different ways. This one by testing points. This one by generating points. Right? But this one's a little bit more familiar. So, it's being able to draw connections like this is useful in, figuring out, relating your new algebraic tools to things that you have more familiarity with. Okay. All right. The difference between these examples. Here, we just kind of recognized, hey, these functions, I happen to already know a relation between them. Right? That's not what happened here. Here, we took the x and y coordinates as functions, and we kind of played around with them strategically to come up with the resulting equation. Okay, so both of these are going to happen, right? Connecting parameterizations to equations is not just this purely algorithmic process. It's going to look different in different cases. So here's a third different kind of example. Let's look at this parameterization. Notice we've got position. So x, y, z as functions of time, right? All three of these coordinates are functions of time. So that's a parameterization. It's a parameterization in three-dimensional space. This represents some particle kind of moving around in space. Position as a function of time. What curve does this trace out? Can I recognize this curve? I'm not going to be able to find an equation for this curve. It's just not going to work out that way. What we're going to do here is come to understand this parametric curve by sort of a different tool, different breakdown. And it goes like this. Let's think about looking just at the x and y coordinates. Keep in mind, in the picture, x and y coordinates. what's its shadow look like in the XY plane, right? So if you look at the whole thing, you've got some point up here on your curve. Looking at just the X and Y coordinates says I want to ignore Z, look only at X and Y. It's like we're dropping it down into the XY plane, for example. Okay, notice that geometrically when we do that, when we project down into the XY plane, we get a parameterization that we're already familiar with. Cosine t, sine t. We know what's going on there. That's a circle. Right? But that was our first example. So what we've learned here is that our curve, whatever this curve is, this curve's shadow down here in the XY plane, its shadow is a circle, the unit circle in the XY plane. Now that still doesn't tell me what the curve itself is, but that's a lot of information. I know that this curve's shadow in the XY plane is easily understood. Okay, so we got a foot in the door. Now we got to figure out where to go from there. The other thing that I'll notice is that the Z coordinate is easy to understand. Right? It's just t. That just says height is increasing at a constant rate with speed equal to 1, right? It's just, the rate of change of Z with respect to t is 1. Okay? So now I actually have a tremendous amount of information about this curve. I know that this curve, as it moves around, whatever it's doing, I know that its shadow is doing this and its height is doing that. And there you can just kind of combine those two facts with your geometric intuition, and it's just not that hard to persuade yourself that you're going to get a helix, they call it. Everybody see how that worked? Again, this is not algorithmic. This is, what we did to understand this parametric curve is pretty different from what we did to understand this parametric curve, which is pretty different from what we did to understand this parametric curve. So I'm adding tools into your toolbox, and make sure to understand how to use the tools, and then when you find problems in your future, you got to think conceptually about which tool is appropriate for this circumstance. Okay. Alrighty. Okay, so let's talk about derivatives. There's a worry here in this question. What's the derivative of a parametric curve? Keep in mind, we're asking a question here to which there, as far as our experience, there is no previous answer. Right? We've never previously defined a derivative of a parametric curve. This is a brand new thing that we're being asked to define. And it's always the case, whenever you're making a new definition, that it's not a matter of, what is it that's etched in stone somewhere, but what should this thing be? Right? There's got to be a justification. Don't just write stuff down because, this is what we did previously, right? Without there being some good reason for it. Okay, so what I'm going to do then is, for lack of better ideas so far, I'm going to actually just write down sort of a rip-off, formulaic rip-off of what we've done before, but I'm going to feel really bad about it, and I owe you now satisfaction on why is it that this thing is useful. Right? This is not the definition of a derivative of a parametric curve just because cosmetically it looks familiar. That's not why. Right, is everybody on board? Okay. All right, so there's our definition, and I owe you satisfaction on what this thing is. So first thing I'll point to. Now keep in mind, another quick thing. Right, we've already talked about this, but important reminder. Oh, come on, eraser. This is not a graph. This formula here for a derivative, again, cosmetically familiar. We remember in Calc 1 that, in the context of looking at graphs, that thing is a slope of a tangent line. But we are not looking at a graph here. So the idea that this would be expected to be a slope of a tangent line, out the window. Absolutely out the window. This is not the slope of a tangent line. Right? So we're going to have to completely from first principles look at this expression brand new with completely open mind, right? And figure out, okay, well, in this new context, what does this mean here? and is it at all useful? So, good news, it works out real nice. And now y'all have seen this expression a million times. I'll point out that this difference, this numerator, is the difference of two positions. Right? That's what parametric curves are. They give positions as functions of time. So the difference between two positions is a displacement vector. And not hard for me to sell, I hope, that a vector that goes from one point on the curve to a nearby point on the curve, especially when, this time difference, right, this h that represents the difference in times, that time difference is approaching zero. These green points are getting closer and closer together. Y'all will remember this kind of story. This time, though, this vector approaches tangent to the curve. And now it also gets really, really small, but then, of course, when you divide by h being small, that h being small, we expect this fraction here to be a tangent vector. So now this is already some satisfaction, right? This in the limit we expect to be a tangent vector to the curve. Now I'll remind you, it's not a slope. We're not saying that it's the slope of the tangent line. The slope is a scalar. That's not a scalar. That's a vector. This is very importantly different. Right? But it is geometrically interesting, right? Again, I owed you some satisfaction. Why is this geometrically natural, or am I just writing down nonsense? And I think this is a little bit satisfying, that it's already geometrically natural in that it's a tangent vector. Okay. All right, so we know what direction it's going. But what's the meaning of its magnitude, right? Does this magnitude, which one of these is it and why? How long is this? What does that have to do with what's going on geometrically or physically? And that's another nice little argument that we can make. Let's look at what happens when we take the magnitude of this expression. And I'm going to gloss over a formality here. Forgive me. Appropriate to Math 212. The scalar at the bottom factors outside of the magnitude. Limits factor outside. I don't want to get into the weeds there. But pretty easy to see, I think, that what we're talking about here is a distance divided by an amount of time. Right? So we've got distance over time, and distance over time is a familiar concept, right? Distance over time is speed. Basic physics thing, right? So we know two things about this our brand new definition. Again, we pulled this kind of out of thin air. Well, okay, now we ripped this off symbolically with no justification. And what we see now is that this is actually geometrically very natural. It's a tangent vector whose magnitude is the speed. That's all physical / geometry talk. And in fact, it's familiar physics and geometry talk. That's exactly the definition of velocity. Day one from our class. Right? The very first thing we did is talk about how vectors can represent many things, and one of them is velocity, in the sense that a vector points in the direction of the velocity, and the magnitude is the speed. Okay. So, we've got a great answer then to the question, right? What's the derivative of a parametric curve? Why can I write this down and it's not just symbolic nonsense? Because it gives us a crazy important, crazy familiar construction, velocity. That's why this is our definition of a derivative of a parametric curve. Okay, is everybody happy and on board with that choice? I'll say yeah. When we compute this, is the answer going to be a vector? The answer is indeed a vector. That's right. Velocities are vectors, and you'll notice the little hat I've got over there. Yeah, totally. Yep. Okay, likewise, the derivative of the derivative. So the derivative of the velocity, analogous argument, that's acceleration. Okay. All right, now, computationally, how do we do this? Here's some bad news. Bad news. This formula, aesthetically familiar though it is actually brand new. We can't just say, oh, cool, same definition in Calc 1. Therefore, I get to bring aboard for free the product rule and the quotient rule and the chain rule and all those good old familiar rules that allowed us to avoid the painful experience of having to compute derivatives from the limit every single time. Did they make you all do that in your Calc 1 class where you have to compute a couple of derivatives, brute force from the limits, right? And then you're like, oh my God, I love the chain rule. Right? It's wow, I don't have to compute straight from the limits. Okay, all that's out the window. Because this is a brand new thing, right? That's not a Calc 1 derivative. So that's a scary thought. Here's the good news. Not hard to show that when you take a derivative of a parametric curve, you are in fact taking a good old, plain old Calc 1 derivative of each of the three individual components. These individual components are Calc 1. They're single output variable as a function of time. These are good old Calc 1 functions and their derivatives, one coordinate at a time, mind you. You get to use the chain rule and the product rule and all your old friends. Okay. Well, that's a relief. Now let me persuade you that this is actually true. It's a pretty straightforward argument. How do we subtract vectors? Well, we subtract vectors one component at a time. How do we divide vectors by scalars? Well, we do that one coordinate at a time. Right? And now, how do we take limits of vectors? We haven't talked about this, but again, this is not this is something that will sweep under the rug in Math 212. But limits you do one coordinate at a time as well. So, and I think that's pretty believable. So anyway, punchline is we take derivatives component wise. That just means one coordinate at a time, one component at a time. Okay, super news. Got to write down some algebraic property. We got a brand new thing, brand new operator, the derivative of a parametric curve. It's brand new, right? So we cannot just take for granted that the derivative of a sum is the sum of the individual derivatives, and et cetera, et cetera. So we got to write down, familiar though they seem, these brand new properties. And good news. A lot of the rules that you would sort of cosmetically hope and expect would carry over from Calc 1. They do. So scalars factor out. Great, right? Derivatives sort of distribute through sums. Right? There's three different product rules. There is a product rule for dot products. Now, again, you never saw this in a Calc 1 class, right? But this is cosmetically kind of looks like our old product rule that we remember from then. It's just now it's about dot products. Not obvious, but it is true. This is something you can totally prove. It's a great exercise. I encourage everyone to do this. You know how to compute dot products. We have a definition of derivatives. Crank it out. Coordinate-wise, right? And then look over at this expression over here. Crank this out coordinate-wise. And then just observe that, sure enough, you get the same thing. Yep.
Isn't the derivative of a scalar 0?
No, the derivative of a constant is 0. So you got to just, and I kind of get where you're coming from, and it's easy to conflate constants with scalars. But scalars are not constant necessarily. Scalars just means they're not vectors, right? Every function that you ever looked at in Calc 1 was a scalar valued function. Right? So they're definitely not always constant. And constants are not always scalars. You can have vectors that don't move. They just sit there. Right? But it's nevertheless, I don't know why. I think maybe it's just because of semantics or something. They sound kind of similar. Yeah. Okay, so I want you all to check for yourselves the product rule for dot products. There's also a product rule for cross products. Way not obvious. But it's true. Right? It deserves to be checked. And likewise, a product rule for scalar vector products. If you have a scalar valued function times a vector valued function, that's a product, and you've got a product rule. Again, not obvious. Okay, What is anti-differentiation? The first thing I want to point out is, and this is one of my personal little soapbox quibbles, but please do not conflate anti-differentiation with integration. It's really, really a lot out there. Right? There are a lot of people that say, it's the same thing. Right? But really, importantly, not. So when we talk about anti-derivatives, I literally want you to think of this as undoing derivatives. That's not what integrals are. If you're not 100% clear on this, I encourage you to watch I have an extra video on my YouTube channel. There's a playlist called Miscellaneous Topics or something like that. And I've got a video there on integrals. What is an integral? And a couple of related sort of offshoots. And if you're not entirely clear on what I mean by this, just watch that video. It should straighten it out for you. Okay, so antiderivatives just means we're undoing derivatives. Good news, also component-wise. You're undoing something that's done component-wise. So, of course, it's component-wise. Right? So, in the same way that velocity is the derivative of position, the antiderivative of velocity is position. Right? It's just like in Calc 1. It's just now these are vectors instead of scalars. Just like in Calc 1, there's by the way, I mean, some of the semantical terms are really, really, soaked into the culture of the language, and so people call this a constant of integration. It just really bugs me. It's a constant of anti-differentiation. Now, that said, I mean, I don't want to be the weirdo who is constantly saying, constant of anti-differentiation, so I sort of accept that people are going to say constant of integration. But I emphasize this is something that comes up when you're doing antiderivatives. And you can say integration constant, but you need to understand as you say that this comes up with anti-differentiation, not integration. Okay. Anyway, but it's just like in Calc 1, just vectors, not scalars. So that's great news. And of course, that's these antiderivatives are done component-wise. Okay, easy to see. A quick little aside, there is such a thing as integrals of parametric curves. I mean, you can just write down Riemann sums. I mean, ultimately, that's what an integral is. At this level. Integrals are Riemann sums. By the way, it's another little offshoot. That's one of the big themes of that little video that I just referred you to about, what is an integral. Integrals are Riemann sums, and that's another thing. It's really important to make sure you really get that. Right? So, watch my video. But so you can write this down. The only thing is, what does this actually represent? It's really not clear. Like, geometrically, what does that thing represent? Well, it's definitely not the area under the curve. Right? And I remind you, you shouldn't have any expectation that it would be. This curve, this parametric curve, it's not a graph. Right? Every bit of intuition that you have about, integrals compute area under curves, that's because in Calc 1 you're always looking at graphs, right? Vertical is the value of the function, and horizontal is the input variable. That's not what we're doing here. So there's no reason to think that the integral of a parametric curve would be at all recognizable. And it's not. Certainly not as the area under a curve. Okay, so don't step on that landmine. It's wildly wrong. You can write down a fundamental theorem of calculus for integrals of parametric curves. And that's fine, right? You just got to make sure to have in your mind a clear picture of what this means. Specifically, the integrand has to be a derivative to be able to interpret this meaningfully, right? I mean, this is not just any old integral. This is an integral of something that is a derivative of something else. So, what instance might that be? Well, look, I mean, maybe it's a velocity, right? This r here, this thing that we're taking an integral of, maybe that r is velocity. Velocity is a derivative. So yes, it is true that an integral of velocity gives you a change in position. Sure, absolutely. But if you're thinking of this as being position, that doesn't make any sense at all in this context. Okay. All right. Okay. All right, now here's a familiar old example. Y'all have seen this kind of thing a million times. The only difference between this and stuff you did in Calc 1 bunches of times is that they're vectors, not scalars. But recall that in Calc 1 classes, or I don't know, maybe physics classes, whatever you might have taken, if they give you acceleration, then you can take an antiderivative to get velocity, you can take another antiderivative to get position, and then as you go along, you can figure out what these constants of integration are. See there? I said it, right? Constants of anti-differentiation. Again, I don't want to be that guy. So you figure these out as you go along, and as a result, you can sort of work your way back from acceleration to understanding position. Right, so I don't want to go through all the little algebraic details. All that algebra is basically familiar. I want to point to two things. One is you're taking antiderivatives of vector-valued functions. Those are done one component at a time, right? Just like we talked about. The antiderivative of cosine is sine. The antiderivative of sine is negative cosine. The other thing I want to point to, and this is a huge problem with Math 212 students, don't just assume that the integration constant, right, is the initial condition. That's not a thing. It just isn't. Right? Now, some of y'all may be thinking, man, back in my Calc 1 class in high school, every time I solved for an integration constant, it was always the initial velocity for this part of the problem. And if it's always true, how come we can't just say it is? And the answer is because it's not always true. Lots of high school classes use functions here that are always polynomials. Polynomials have antiderivatives that always have a factor of t in them. And if there's a factor of t, then of course that turns out to be 0. And so if you're looking at that very restricted category of cases, if this were in fact always 0, then yes, the initial condition would be the same as the integration constant. That's just not true in general, though. There's plenty of functions whose antiderivatives are not always 0. And here's an easy example, right? Sines and cosines, right? The antiderivative of sine is cosine, which is simply not 0 when you plug in t equals 0. Okay, so the important point here is whether or not you get the correct answer for your integration constant isn't the point. Right, just a quick aside, sort of reminder, what do we do in this class? Why are we here? What am I looking for on exams? I'm not looking for the answer. Right? I'm not interested in whether numerically, but I got the right result at the bottom of the page and I just did it a different way that my high school teacher showed me. That's not what we're talking about. What I'm interested in looking at on your exam papers is, does your argument make sense? Is your argument actually valid? That's what we care about. Right? And independent of whether that argument, the old high school argument of it's always the initial condition. Independent of whether that gives you the right answer, it's always invalid. Sometimes invalid arguments give you right answers. Right? But it's the argument that we care about, not the answer. So I just want to make sure that everybody gets a very clear picture. If you do this kind of thing, so in other words, if you don't do the calculation, if you just kind of, say, this C and, the C is the V naught and just kind of move along, even if numerically you're right, you're going to lose a lot of points because your argument is worthless. Everybody, okay, so I think everybody gets it, but anyway. Okay. Alrighty, ditto for the next step, of course, this integration constant. You got to watch out for that thing. That thing there is not always 0. Okay, so that's 12.5. We're going to move on to section 12.6 now. We're actually going to skip a lot of section 12.6. The syllabus, we made a decision early, right before the start of the semester, that we're going to de-emphasize section 12.6. Long story. I don't want to bother you with the history on that. But so very little of what's in 12.6 is actually going to be fair game for the course. There's a couple of things in 12.6 that we need for future sections, but most of section 12.6 is a really interesting kind of digression, kind of offshoot that's not really part of the prerequisite trail for the rest of the course. So we're pretty much going to skip most of 12.6. I'm going to show you the couple of things that we are going to use for later, and then we're going to move on to the next thing. So two things that we need. First of all, if you have a parametric curve, keep in mind a parametric curve, position is a function of time. Remember what differentials are. Differentials represent little changes in whatever it is that you're looking at, right? So back to Calc 1 in a graph context, right? So there you go. So y is a function of x. dy represents how much does y change, or the linear estimate of how much y changes. dx represents how much does x change, right? And then the proportion between the change in y and the change of x, that's how we talk about derivatives. Okay. All right. Well, if you're looking at a parametric curve, what would or should dx mean? What does it look like geometrically? Well, it's going to be actually surprisingly familiar. In the same way that dy represents the change in the output of the function, dx vector represents our linear estimate of the change in the output of the function. It's just that now the output of the function is position, right? So it's the whole position. It's all of the coordinates of your position on the parametric curve. That's what a parametric curve is. Position is a function of time. So dx is our linear estimate of your change in position on the parametric curve as a function of time. And just like you might expect, dx is x prime dt. That just says displacement is velocity times time. Very natural. Don't forget that x prime, color choice, hang on. X prime is velocity, right? And so we have a pretty nice formula for dx. dx is v dt, v being velocity. This is going to be a useful thing to talk about. This dx vector, I like to call this, by the way, the position differential, because it is a differential, change of, right? Differential of position. X. Okay, so it's ultimately no big deal, but it's something that you kind of have to think through. You have to, in the context of parametric curves, not graphs, right? You got to kind of reconceive of what that means. It's not a change in height. Height is the output value if you're looking at graphs. We're not looking at graphs, right? So it's just a differential of position. All right, next thing is let's talk about ds. What does ds mean? ds just represents the magnitude of that dx vector. Oh, here, I'm messing up my colors again. ds represents the length of the dx vector. Keep in mind, these are linear estimates, right? So the dx vector does not perfectly track the curve. It's a little differential tangent vector. The curve actually kind of bends away, probably, from that linear estimate. So doesn't perfectly track the curve, but nevertheless, the magnitude, geometric appeal, the magnitude of that dx vector in representing the length of our position differential maybe kind of should be thought of as representing the distance traveled. Let's see, where's my colors? Here we go. The distance traveled along the curve. How long, you might say, is this little piece of curve? Again, as a linear estimate, right? It's not the actual thing, but it's a linear estimate. Okay. All right, so both of these things are going to be used quite a bit later on in the course, various times. So dx is the position differential. ds is the length differential. And by the way, just remember, length is speed times time. And I want to point to the notation. There's another little new notation that we haven't used before. We're going to use little v with no vector hat over it to represent the magnitude of the velocity vector. So it's just convenient. I mean, look at all the sort of like the paraphernalia surrounding the v there, right? We got to put a vector hat and then the double bars on both sides. It's a lot to write down. When I just want to talk about speed, right? The magnitude of the velocity. It's just speed. So be aware. You got to be careful in this class as to whether you're talking about v representing the velocity vector. You got to put the little hat, the little arrow head hat over it. Versus if you want to talk about speed, you just write v with no little arrow over it. Okay. And we're going to skip the rest of section 12.6. It's the next 3-4 pages. I kind of lost count there. But we're just skipping right over that. Okay, so moving along. Surfaces in R3. No surprise, this being a multivariable calculus class, we're going to be doing a lot of business in space. A lot of business in 3 dimensions. We need to understand surfaces because surfaces are pretty interesting things in 3 dimensions. Here's another way to say it. Very often we're going to have equations that relate 3 different variables. We need to understand what the solutions to such equations might look like. So what is the solution to an equation that involves 3 variables? And I will point out to you in a Calc 1 class, there's usually next to 0 attention given to this question because Calc 1's about single variable functions and you have output as a function of input and it's all on the plane. It's all 2-dimensional, pretty much. Okay, so if I were to show you an equation involving 3 variables and ask you what surface does this look like, we've never hardly ever considered that question before. Maybe you had a Calc 1 or Calc 2 class that maybe touched on that a teensy-weensy little bit. So we've got to develop some tools to figure out how to do this. There are different ways to understand surfaces in R3 or equations of 3 variables. And I'm going to show you various different tools for understanding them. So let's just dive in, do one at a time. The first thing I'm going to do is talk about this idea of a cross-section, which the book calls a trace, which I don't know, I feel it's a little obscure. Cross-section, I think, is everyone knows what a cross-section is. If you have a thing, right, a cross-section says take a slice, maybe this way, whatever. You take a slice and you look at what does that slice look like. So either of these terms is fine. Okay, how do you do that? Right? What's algebraically? How do I actually take a slice of something? Here's the idea. Suppose I have some equation. Now, at this point, we have no idea what that equation represents. By the way, if you already know, just kind of forget that you already know. Right? What is that thing? I don't know. It's some surface. Who knows what that surface might look like? It's some sort of maybe it's kind of roundish. I don't know. But some wacky surface. Here's the idea. If I want to understand what happens when I take a slice, if I cut through this thing, if I want to know what its cross-section looks like in some plane, that plane has an equation. Right? The cross-section that I'm interested in, whatever that cross-section is, that cross-section represents points that are in the unknown green surface and this known blue slicing plane. I'm looking for points that are in both. That means I'm looking for points that satisfy both of these equations In other words, I need to take both of these equations, the one that I'm interested in, and then my new equation z equals c. Whatever altitude I'm taking my horizontal slice at. And I've got to work with both of them. And it's tempting to say that makes the problem harder. I started with one equation, now I've got two equations. These equations I'm getting buried in equations here, right? But it's not harder, it's actually easier. Because it allows you to eliminate a variable. And so notice in here, if you take this formula for z and plug it into there, then that equation becomes simply x squared plus y squared equals c. So by taking this cross section, as we've done here, we took an equation involving three variables, and we've reduced it down to an equation involving two variables. And equations involving two variables we're pretty good at, right? We did a lot of that in Algebra 2, or whatever they call Algebra 2 now these days, right? So we turn a hard problem into an easy problem. By the way, just as a cultural point, I think it's important for everyone to realize that this is a common practice in math. If you want to tackle a hard problem, very routinely, the way you tackle hard problems is you give yourself some additional assumptions, and which turn the problem into an easier problem. I've got more tools to work with. I get to assume this, I get to assume that. So turn your hard problem into an easy problem, and then having done that, interpret, okay, well, technically I didn't really solve my hard problem, but I solved a related easy problem. How are they related? This extra assumption I gave myself, what does that mean about the answer that I just found? How does the solution that I just found relate to my original thing? And what I get in this case, of course, is that if I understand that thing, if I understand the solution to this, simplified problem, that is telling me what one of my cross sections looks like of my original surface that I'm trying to understand. So you'll see this all over the place in math at all levels. We turn hard problems into easy problems, solve the easy problems, and then kind of try to work it back and figure out what that really means for us. Okay. So what we've got then is that when you look at a cross section in that plane, you get a circle. And now I appeal to your algebraic intuition. If you look at a cross section in a different plane, well, these numbers change a little bit. That means this number changes a little bit, and that means that your interpretation of this algebra changes a little bit. In this case, with z at a lower altitude, you get a smaller circle, and so a smaller cross section. So we've learned something. We still don't know 100% what this thing actually looks like, right? But we do know that horizontal cross sections are circles that are getting bigger as you move higher. And that's a tremendous amount of information. It's again, we still have some unknowns, but that's a lot of information. We're looking at a sort of a stacking of a bunch of circles sort of on top of each other. And that's a lot more than nothing. Okay, so you can do this in different directions. By the way, these pictures do get hard to draw. Got to practice. Oh, by the way, I wanted to point out to everybody, if you're thinking to yourself, okay, yeah, but I'm no good at drawing pictures, right? Time to get good at it. It's unavoidably critically useful in a class like Math 212. Math 212 is not a class where you can take either a geometric or an algebraic approach to understanding things. Math 212 is a class where understanding the algebra is essential and understanding the geometry is essential. That is part of the class. It's not an alternative. It's an and, not an or. Right? So we need to get everybody to where they are better at understanding things geometrically, and being better at drawing will be very helpful to that. So come to my office hours, and I'll show you my little tricks. I'm not an art expert, right? I'm not that bad, but I can show you the few tricks that I know that I think are really useful for drawing math pictures. Yeah.
I was just gonna say, like, for instance, some of the problems that we're going to work are pretty easy to visualize. But then actually writing them, like drawing them out.
Yeah,
is
yeah.
very difficult.
I know it. So that's a skill that everybody needs to sort of work on. And it's I don't know, it's like swinging a golf club. Someone's got to show you how, and then you've got to practice it. Right? More than I have, because I'm terrible at that. But anyway. Okay. So let's go through our process again. Starting with our original. Right. So we have x squared plus y squared equals z. That was our original equation. Trying to figure out what this thing looks like. Let's look now at these kinds of planes. Sort of vertical planes. By the way, notice perpendicular to the y-axis. Right? So what do those cross sections look like? Well, I get to write down both my original equation and my new slicing equation. I want to know what happens when I look at both. Namely, I want to plug that into there, which makes the algebra look like this, and this is something familiar. That's another equation involving two variables, x and z. Z is x squared plus some constant, whatever that is. And that's familiar. Z equals x squared plus some crazy constant. That's a parabola. We all know that that's a parabola. So this mysterious surface that we're trying to understand, its vertical cross sections perpendicular to the y-axis are parabolas. And we can see actually a little bit more even. What is that constant doing? The c squared. In fact, let me be more clear. This plus c squared. What's that really doing? Well, y'all know, again, flashbacks to Algebra 2. Whatever constant you have in there in that equation, that's telling you the vertical shift. How much is this parabola being shoved up above the, its vertex is being shoved up above the axis. So that's telling you how much the vertex gets shoved up. And notice it depends on. Here, let me clean up my picture a little bit. It depends on c. Whatever that c is, the bigger c is, the bigger the upshift is. The upshift is c squared. You can also see that, no pun intended, that upshift is always positive, right? So it's c squared. It's not just c. The upshift is positive when c is positive, but it's also positive when c is negative. So it shifts up kind of on the right side, and it sort of shifts up on the left side too. So what have I learned here? Well, I've got more information now. I've got another, and again, these are hard pictures to draw. Come to my office hours. I'll show you my tricks. Right? But we've got a different sort of perspective now on what this surface looks like. We know it's got circular cross sections, and we know that it's got parabolic cross sections slicing the other way. And now think for yourselves about what happens when you take cross sections perpendicular to the x-axis. Right, perpendicular to the x-axis, your cross sections are going to look like this. Those cross sections have certain equations. They plug into the original algebra in certain ways. You get certain results. I mean, you got to think through the whole process, just like we've done here. But it gives you yet more information. So, all together, then, what does our surface look like? You can kind of, depending on how good your geometric intuition is, you might have enough information to kind of piece it together. So this strategy for understanding equations of three variables is called cross sections or traces, and it's a tool for your toolbox. Okay. All right. Let's see here, and I suppose this is this is a Friday, and rather than hold y'all a minute late, I'm going to let you go a minute early. So see y'all later. Have a good weekend. We'll pick up here on next time. Have a good one.